All right, welcome to week 6, part 4, our fourth and last discussion of the NumPy module and its ND array, n-dimensional array collection type. We've looked at two different ways of obtaining subsets of ND arrays. We've looked at using slices on rows and or slices on columns. We've also looked at Boolean indexing for accessing subsets of a multidimensional ND array. In this section, we're going to take a look at what are called fancy indexes or integer indexes, which gives you a different kind of flexibility for accessing subportions of an ND array. We're also going to introduce some statistical functions that NumPy provides, and I'll mention just a few other categories of other functions that NumPy also provides. This is going to be the last new material for the course. We'll also have, in week 7, a brief review of the topics that we've covered during these 6 weeks, and then we will wrap things up with a final exam during week 7. All right, so onward ho. Here is, once again, our AN array, in which we most recently modified these 3 items using our Boolean index to set those to 3. Using fancy indexes involves using a list of integers to specify which columns you want, or which rows you want in this case, and you can also specify the order that you want those rows in. So if I were to say, let's think back to using slices. If I were to say 0:2, that would access all of the rows in AN from row sub 0 up to but not including row sub 2. So it would give me the first 2 rows of the array, of the ND array AN, right? But I get those in that same order. I get the row sub 0 first and the row sub 1 second. Using fancy indexes or integer indexes, not only can I select which rows I want, but I can also specify the order that I want those rows in. All right, so here's my AN ND array. And now, using a fancy index, which is a list of integer row subscripts, I can say, show me row 1 first, and then row 0 next. So I'm going to get the same 2 rows, but I have changed the order of those rows in this result. Now, I want to be clear that AN itself is not being modified. If I wanted to obtain a copy of just those 2 rows in that order, I could do something like this. AN, let's call this AN 10, because I want row 1 followed by row 0. And I'll say AN sub 1, 0. Now, I don't want merely a view on that part of AN, so I'm also going to throw in my copy method. All right, so AN is what it was, and AN 10 is a copy of the first 2 rows of AN, but in the reverse order. Okay? By the way, you may remember that we use the ID function to look at the IDs of objects, and I can look at the ID of AN and the ID of AN 10 to confirm that these are different objects. They have different IDs. So that's one example of a fancy index. Now, if I want to get certain columns in a different order, then I do need to specify that I want the rows, which I do using regular slice notation. Okay, so recall that in slice notation, colon all by itself is equivalent to 0:3 in the row direction. I want everything from row sub 0 up to but not including row sub 3, or I can just say colon for all the rows. And this time, the columns that I want are column sub 3, sub 2, sub 1, and I want another copy of column sub 2. So not only can you change the orders of columns or rows, as we saw up above, but you can even request duplicate copies of rows and or columns by using fancy indexes. All right, so let me do this again. So here's AN. That's what AN contains. And here is AN, all rows, but columns sub 3, sub 2, sub 1, and then sub 2 again. All right, so I have column sub 3 first, then sub 2, then sub 1, and then another copy of column sub 2 out here. All right? So that's what fancy indexes are about. You can not only select, but you can also change the orders of rows and or columns. If I were to say AN sub, and then in square brackets, 1, 1, 1, 1, 1, now I'm going to get 5 copies of row 1. Row sub 1, which is, the second row. All right. So those are the 3 indexing methods that you can use for accessing subportions of an ND array. You can use slicing, you can use Boolean indexes, and you can use fancy indexes. And those give you an enormous amount of flexibility, not only over which rows and columns you select, but also the order in which you obtain those rows and columns. In addition to just storing numbers and allowing you to retrieve numbers, and obviously you could use things like loops to step through the items in this ND array. There are also a variety of ordinary math functions that operate on an element-by-element basis within the array. Absolute value, square root, e to the x, log of x, ceiling, floor, sine, all the usual trigonometric functions. And there are a bunch of statistical methods that are predefined, as well as linear algebra facilities. So you can use the linear algebra facilities of NumPy to do things like solving sets of linear equations. Let's take a look at some of these statistical methods. Here I'm going to do something called setting the seed of this random submodule to 0. The seed is the value that kicks off the generation of the random values that are produced by random number generators. And by setting the seed to a specific value, that ensures that the next random numbers that you generate will be in the same order each time. So it's often done that you will set an initial seed for the random number generator so that each time you run your program, you'll get the same sequence of so-called pseudo-random numbers. All right, so I've set the seed to 0. Now I'm going to create a... Sorry about that. I hit the page down button by accident. So let me go back and try this again. I'm going to copy and paste this statement. And then I'll explain what this statement is doing. Okay. When we created the AN ND array originally, maybe I should be calling this one AN2 to differentiate it from the AN that we had before. We used a function named randn that generated random draws from a standard normal distribution with mean 0 and standard deviation of 1. This time I'm just using a function called plain old rand. I am not going to get draws from a standard normal distribution now. I'm going to get draws from a uniform distribution on the interval 0, 1. So any floating point value in that interval from 0 to 1 is equally likely to occur from this random draw. Rather than creating a two-dimensional array of these numbers, I'm just creating a one-dimensional ND array of 14 values. And I'm going to round these things off to 2 positions after the decimal point just to make things fit neatly on my screen. Okay. And here is what AN2 looks like. All right, so I've got 14 random draws from this uniform distribution on the interval 0, 1. And because I set my seed to 0, this time I get exactly the same sequence of values in this ND array that are shown in my notes. This is a one-dimensional array. The shape shows me... well, AN is still a two-dimensional array. AN2 is a one-dimensional array with 14 items. And I can ask for various statistics about this AN2 array. I can ask for AN2's sum. I can ask for AN2's mean value by computing the sum divided by AN2.shape sub 0. Okay, the sum divided by the number of elements is going to be the mean value. Or I can just use the built-in mean function within the NumPy package to compute that same number. All right. Now, the mean value of AN2, ought to be, I'm going to redo that. The mean value of these random draws on the interval 0, 1 should be 0.5. However, this sample is so small that I happen to be quite a ways off from 0.5 in this particular case. My minimum value in this list of this ND array of 14 draws is 0.38, which I hope you'll agree is pretty far above 0. And the maximum draw that I got was 0.96. So you can see that the mean of the values that I did actually draw is going to be skewed above 0.5 probably. If I ask for the variance of this data set, now the theoretical variance for the uniform interval on 0, 1 is going to be 0.08333, which is 1/12. But the variance for this particular sample is quite a ways off from that. And the standard deviation is simply the square root of the variance, which theoretically ought to be 0.288675, etc., etc. There's more digits there. And again, the value that I get is different. Now, these values are different randomly. Each time I draw a random sample of 14 and recompute the mean and the min and the max and the variance and the standard deviation, I'm going to get different values for each sample that I draw. But as I draw more and more and more and more samples, the mean of those samples and the variance of those samples and the standard deviations of those samples will approach these theoretical values. In fact, if I draw 1,000,000 values, that sample size is large enough that my sample mean and variance and standard deviation ought to be getting pretty close to the theoretical values. So let me say, well, now I'm going to say AN3 np.random.rand and 1 0 0 0 0 0 0. So I want 1,000,000 of these random values. Oh, I said dot instead of equals. Sorry about that. So let's put an equals or gets operator in here. So AN3 gets these 1,000,000 random values, and I can confirm that there are 1,000,000 random values in there by asking for the length. Well, actually, since this is an ND array, I can also ask for the shape. Okay, so there are 1,000,000 values in here. I don't want to print those out because that could possibly be so much data that it will hang my window and I'd have to kill the window and start over again. But if I now compute AN3's mean, I'm pretty close to 0.5. I only deviate from 0.5 down in the 4th decimal place after the down in the 4th decimal place. My minimum value for this large sample size is not 0, but it's getting pretty close to 0, 7 times 10 to the minus 7th power. And my maximum value is not 1, but it's getting pretty close to 1. My variance for this sample is pretty close to 0.8333. All right, it's a little bit off down in the 5th decimal place, but it's pretty close to 1/12. And consequently, because the standard deviation is simply the square root of this, the standard deviation is pretty close to the theoretical value that I should be getting. Okay, so that is a very quick look at another of the random number generators, this time generating random numbers from a uniform distribution rather than a normal distribution, and a few of the simple statistical functions, mean, min, max, variance, standard deviation. I did want to take a look back at our medical data that was in this. Now I've forgotten, okay, I have forgotten my variable names, but all is not lost because of course I can ask to see vars, and my medical data from my doctor's office is in this variable ACSV. I wanted to do a couple of examples with this data. ACSV. This is my age, height, weight data. And I can do statistical analyses on these columns. I can say ACSV sub. Well, to get column sub 0, which is the ages, I want all of the rows and then column sub 0. All right, so that's going to be my ND array of ages, and I can ask what is the mean age for people in this medical practice, or I could ask for the heights in inches of these people and find out what the mean height is. And likewise the mean weight. Let me go ahead and just change the, okay, well, let's look at column 2. Not weight. Weight is not a function. Weight is the column, and here I'm asking for the mean weights. 168. Now, if I take a look at the data, you'll notice something that we probably ought to have in this data. It may take you a minute to observe this, but we don't have any distinction between gender. We don't have men and women separated. And obviously there's going to be a relationship between the height and the weight, and there will also be some relationship between the gender and the height, and therefore the weight as well. I believe that the average height of an American man is about 5'10", and an American woman is about 5'6" or 7. I'm not 100% certain of that. But let's, well, we could guess at what these genders are. Let's not bother with that. I also wanted to illustrate one example, and I forgot to put this in the notes, but I'll just go ahead and do it live here. What if I wanted to visually see the relationship between height and weight? Now, there's not going to be much relationship here between age and weight, or age and height necessarily, but I can use my my PLT matplotlib object that I created and say PLT dot line, pardon me, PLT dot plot the, let's have the height as the x-axis, and that's going to be ACSV sub all columns, all rows, pardon me. Column sub 1 is the heights, and I want to plot that versus ACSV colon 2, which is the weights. Okay, so I'm going to create that plot, and it's thinking. There we go. So that generated a plot. Now, the plot, it turns out, if you play with if you play with matplotlib, you'll discover that you have to say plot.show to actually see this thing on the screen. All right, so I do plot.show, and here's what I have. Okay, this is this is a mess because the values are being shown in the order. Oh, I didn't want a line chart. I wanted a dot chart. All right, so that was rather dumb of me. Let me try this again. Let me kill off the plot. Okay, I have to actually close the window. And what I forgot was my third argument that specifies how the dots should be displayed and whether they should or should not be connected by a line. By default, what we get from this style of plot is a blue line connecting all the dots. And I don't want a blue line, I just want dots. So let me redisplay that, and as our third argument, I'm going to say blue, and then let's use an O so that I get O's for dots. And now when I do my plot.show, there we go. Now it looks a little more like what I had in mind. So we see here the weights on the vertical axis, the weights on the y-axis, and the heights on the x-axis, and you can see that there is an approximate linear relationship between those. If we wanted to get into more advanced stuff, which we don't have time to do in this course, we could do a linear regression. We could find out the significance of the parameters in the linear regression, etc., etc. All right, but that is a brief introduction to creating and using two-dimensional arrays in rows and columns in NumPy using ND arrays. And that's it.